Hi, good morning. And today is 1 minute past 8, and it's the 22nd of July 2021. So every week, Zimmer Peacock does this, let's say, live webinar for our members of our ZP Developer Zone. So let me just sort of dive straight into it. We've got a lot to cover today, so I will sort of dive straight into it. As you know, every week we have a webinar. We have our ZP Academy, which has got free courses for people who want to learn about biosensing. We do the webinar. We have quite a lot of collaborations running, and we post jobs, including internships. So we have, several sites running, or we have several sites. We have one in Coventry. We have one in London. We have several in Norway, and so we have these sites, and we have internships, and we offer jobs, and we have visitors. So there's a lot of collaboration going on and jobs. And as I say, you guys are members of the Developer Zone. So this live stream forum is powered by, this live stream webinar is powered by our forum. So in our forum, if we get interesting questions, we ask people to post them onto the forum, and we then kind of address them. And I do appreciate that some of these questions now, members of the forum, like Ali or Aftab, will kind of come in and answer some questions. I also see that Hasim's online at the moment. So Hasim is one of our ZP Developer Zone members. It's almost describing him, he is the founding member. And he's actually with us in Coventry at the moment, so which is in the UK. So the questions that came in through the forum this week were, how do I design a custom impedance analyzer with inbuilt cartridge? There we are, Aftab's just joined us as well, which is cool. One of the other questions was a lot of questions around the EasyFlex. So I'm going to talk a bit about the EasyFlex, which is for wearable applications. We had a question come in from Selsuk about how to detect sort of analytes and a limit of detection, how to kind of get a lower limit of detection on analytes with immunosensor type applications. We had some questions around, follow-on question around electronic tongues, which I appreciate Aftab also answered on that, so I do appreciate, cool. Hi Nagoon. And Aftab also answered that as well, which I appreciate. And also we had a new member and some questions about nitrate and ammonium biosensors. So I will touch upon that today. So there's quite a bit to cover, and we'd like to keep these things within the sort of 30 minutes. So we did get a lot of questions about the EasyFlex, and the EasyFlex is this kind of flexible electronics for wearable applications. And when I looked at the questions, it's, do you have firmware programmed before shipping? And the answer is yes. And now the questions start asking quite analytical electrochemical questions. Can we do differential pulse voltammetry? Can we do cyclovoltammetry? What's the resolution of the voltammetry? Can it run for 2 hours? Now, what this question is, what these questions are, is they're really asking, is this a potentiostat? And the EasyFlex is not a potentiostat. The way we set it up is we set it up, essentially in amperometric mode. So it can't do differential pulse and it can't do cyclovoltammetry. It can if we do program it, but standardly we don't do that, let's say. So the reason I sort of bring that up now is because let me just click here. So the reason I bring that up is this is the device that the person's interested in, EasyFlex. Now on the website we do have a lot of information regarding the EasyFlex. So we put a lot of videos out there, a lot of PDFs, and I'm starting to get the EasyFlex I think is best for startup companies with engineering teams. So if you're a startup company and you have an engineering team with some mechanical engineers and some electronic engineers, and maybe some data and then some sensor guys as well, it's a good product for you. But if you're at a university and you're essentially kind of on your own on the project, then I don't think it's such a good product for you. So I'm actually going to suggest that in an academic situation, if you want to do a fairly quick start on doing wearable sensors, maybe the EasyFlex is not the best technology for you. So what I want to suggest is actually what I think the best technology for people trying to do wearable applications is actually to use the Sense-It Smart. Now, the reason I'm showing this image here is you can see that it's not inconceivable that actually the Sense-It Smart works really well with Androids. So you have an Android, you plug the Sense-It Smart into it, into which you then can plug a screen printer lecture or a sensor. So the Sense-It Smart is pretty good because it's a fully functional potentiostat, and it's small. It's pretty cool. But the problem with it is the sensor actually goes into the Sense-It Smart. So what I'm suggesting is, if you're trying to do a proof of principle in a more academic or sort of budget constrained environment, my advice is get a band like this so you can put the smartphone essentially on yourself. Get a Sense-It Smart. Now you have to fix the biosensor to yourself, so this becomes kind of your problem. But what I'm going to suggest is this, that obviously we have a whole range of biosensors, from glucose to oxygen to lactate to nitrate to ammonium. They're all in there, and they all look a bit like this. So what I'm suggesting is, in fact, we'll make a cable that goes from the Sense-It Smart to our biosensors. Now the good thing about the Sense-It Smart is it can run all of these biosensors, and in fact we actually have some videos where you can see how to do the settings on a potentiostat for any of these biosensors. So rather than, if you want to do a wearable application and you are at a university or somewhere where you don't have the resources of a startup business, startup business generally will have at least an engineer to support. If you don't have that, then I would strongly suggest to actually go with the Sense-It Smart, especially if you want to do things like differential pulse voltammetry and cyclovoltammetry. And so what I'm sort of thinking is, you can essentially strap the Android onto yourself using one of these sports bands. You can put the sensor onto your skin. You can run a cable now, between the Android and the biosensor, and don't go down the route of EasyFlex. EasyFlex is sort of needs more engineering support. And actually, so what we've done is, I added it yesterday, is we're willing to ship the Sense-It Smart with a cable that will allow you then to kind of have the sensor at a sort of distance from the Sense-It Smart. So in summary, I mean, I think what I like about Zimmer Peacock, obviously, is that we think, okay, we do have a whole range of products, but when we look at what people are trying to achieve, we do try to think, what's going to help this person kind of get to where they need to be in the shortest amount of time. And if it means, saying don't do this but do that, then we will suggest it. So Sense-It Smart is great. Plugs into the Android. It does differential pulse voltammetry, does cyclovoltammetry. It runs all our biosensors. The problem with the Sense-It Smart is the sensor is meant to plug straight into the Sense-It Smart. But of course, if we make an adapter cable, then essentially we can have the sensor remote from the Sense-It Smart. And now, put the Android phone on a sports band, affix the sensor to the skin. They're at a distance from one another, but as long as we put a cable in with a pack, then you can run the Sense-It Smart remote from the biosensor. I think that's the best way of doing wearable applications. We're trying out some ideas rather than going down the EasyFlex route. So that would be my kind of suggestion. So I'm going to move on now to we had another question that came in this week, which was asking about how to make a built-in cartridge holder. So what I'm going to do is I'm just going to grab, I realize I might have to slightly increase my window size a bit, just very quickly. Right, so I'll show you a cartridge holder. So this is a device that we've developed. It's doesn't look very pretty like that, but this is a kind of cartridge, and there's a cartridge holder here, and we've had to develop the cartridge holder so that the cartridge can kind of clip in and out. So I do understand the question. So this is kind of the sort of thing that the inquirer is asking, is how do I make a holder to take cartridges? So that's an electrochemical sensor. It needs to go into the device, and so the questioner is asking, how do I make a cartridge holder? All right. So let me just shrink that back down and sort of jump back into the question a bit more. Right. So the question they're asking is, we have a Keysight impedance analyzer, which I've just brought a picture up. It doesn't have a built-in cartridge holder. Can you custom design an impedance analyzer that has built-in slot? So the quick answer is I suppose we can, because this is an example. It's not the prettiest looking device, but this is an example of a electrochemical instrument with a cartridge holder. I mean, this one is, the guys who follow us on the channel quite a bit know that this one is actually designed for analyzing the breath. But it is a electrochemical instrument with a cartridge holder. That one is actually for analyzing the breath. So the quick answer is, yeah, we can do stuff like that, but I'm sure many of the other people in the developer zone can also do things like that. Now, their question is how to make a cartridge holder. Now, my first thing is, I think you really need a proper impedance spectrometer. The difference between an impedance analyzer, I would say, and an impedance spectrometer is probably really the software. An impedance analyzer kind of ends up giving you very raw signal, whereas an impedance spectrometer converts the signal into something that's more interpretable. So I think the first thing you actually need is you need to start transferring off the Keysight and get onto an impedance analyzer, an impedance spectrometer. So this is the Anapot. Now the Anapot has a plug in the back, and into that plug, this is the Anapot EIS. Into that plug, and we can put cables. So there's plenty of cables available. It's actually a LEMO connector. Any of you engineers know that LEMO connectors are pretty good connectors. And now we have a LEMO connector, a 5-pin LEMO connector that connects into the plug and ends in banana plugs. These banana plugs have got crocodile clips on them, but they're 3mm banana plugs. The reason I bring that up is because it's not too hard to actually then think, all right, to make a holder for your cartridge or your sensor, and then you can just actually, this holder that we've got on our website, it's got 3 ports on the back of it, so that we can essentially, and I probably have that on the next slide, I'll show you what I mean. Because what you can do, I've got it on this slide, so you can plug the cable into the analyzer, and then those 3mm plugs can all plug into that holder. So I think if you're trying to do a custom connection to a new cartridge that you're designing, first thing is you probably need to come off the impedance analyzer and come onto an impedance spectrometer. The big difference between analyzers and spectrometers, I'd say, was the software. As a proof of principle, I think you need the spectrometer, the cable, then you can just make any adapter you want. As long as it can take 3mm banana plugs, you can definitely make those kind of adapters. So I can understand that you really want to get to something as elegant, let's say, as this click-in device, but in some ways you have to walk before you can run, and I think you've got a few steps on the way, and the first one is get onto the spectrometer, get a cable which connects into the spectrometer and ends in 3mm banana plugs, and then you can plug those banana plugs into, then you can start making an adapter here. See, that's it's easy enough then to just start varying that and making the adapter that way. So that would be my kind of advice around that. Right. Just out of interest, I thought I'd mention this as I went through. I think the convention that we follow, and I think it's an ISO standard, is the cable to the working electrode we make red, the cable to the reference electrode we make blue, and the cable to the counter electrode we make black. So just to sort of the community, just stick with that convention so that we don't get kind of confused with one another. So I was showing on the previous picture, I was using colored lines, and I was definitely following the convention that I'm showing on this page as well. So not a big deal, but just it might be useful to kind of follow that convention. Right, I'm sorry to have been speaking so fast this morning. We do have a fair amount to get through, so I am going rather quick. Now the electronic tongue question that kind of came in last week had a follow-on question, and Aftab correctly answered it. He was saying Aftab's response was you probably need parallel potentiostats. So the part of the question is, the questioner last week was asking, how do I test saltiness? And we said sodium sensor, it's quite straightforward. How do I test sourness? That's a pH sensor, quite straightforward. How do I test how do I test sweetness? And we suggested a glucose sensor, for example, and that can be done. Now the saltiness sensor and the pH sensor, they're ion selective electrodes. So they fall into the same category as things like a nitrate sensor or an ammonium sensor. They're ion selective electrodes. The glucose sensor is an amperometric sensor. So now let me dive into this. So he wants to know about the kind of electronics that he needs to do this. So I'm only going to answer the question on 2 of your 3. I'm going to say to you, it's quite easy to do the pH and the sodium sensing in parallel at a low price. You can do all of them at a high price because it's called a parallel channel potentiostat. We sell them on our website and we use them an awful lot. So there's a low cost answer and there's a high cost answer. The high cost answer is you just need a parallel potentiostat. But if you're really a company and you're trying to actually develop a product, you do need high-end parallel potentiostats in your development, but in your product you don't want them. But let me show you what we have for ion selective electrodes. This is not this. So let me show you what we've got anyway. That might be a start. So this is something that we have on our website. We call it the ISE for OEM. Not very catchy, but ion selective electrode is an OEM type solution. OEM just means original equipment manufacturer. So what we have here is a thumb-sized board, and we've configured it to measure ion selective electrodes. Now, what makes it sort of, let's say, more interesting is actually we've really been able to drop the price down here. So this USB powered and USB communicated with board, a single channel on it, we can do at 250 euros. And so, sort of 2 channels, 500, 3 channels, 750 euros. Now, I like this. Now, if you want full functionality, then the Sensit Smart is a good option. The Sensit Smart retails at about 855 euros, but it's single channel. So this is a single channel device, at the moment only configured for, let's say, sodium sensors and pH sensors, those ion selective types. But what's good about it is the low cost. Now, because it's USB driven, you essentially just, the more USB ports you have on your device, then the more of these you can drive. So you could actually drive, pH and sodium at the same time. So let me just dive into this a bit deeper. God, I've forgotten already what this is, but this is not forgotten what it is, I've forgotten the brand name of this. But on our website, and I'll put a link in a minute, we do have details about how to communicate with that board. Because what you need is, you need what's called a terminal program. The terminal program connects to the USB board. We put in the settings. Once you get the settings right, there's communication between the two. And essentially then whatever the board is seeing in terms of pH or the voltage, because pH equals voltage or sodium equals voltage, you're going to get the raw data, and then you can sort of basically plot it in, it's a CSV file output, and you can plot it in something like Excel. So I think if you want to have a very, very easy experience in electrochemistry, then you really want potentiostats. The lowest cost potentiostat on the market is the Sensor Smart, I would say. If you want to truly run 3 sensors in parallel, you can use a multi-channel potentiostat, and we have those. If you want to do it at a lower cost, then the best option at the moment, I think, is this, the option that I've been showing here, because of its price, but it's only set up at the moment to do ion selective electrodes. It's not set up to do the glucose sensors, so you can only do 2 of the 3 that you want to do. It does have the capability of doing amperometry, we just haven't done the firmware well enough to actually implement it. So that would be my kind of low cost option if you wanted to kind of start getting into at least using the ion selective electrodes. And we've tried to make it at a price now that, you know, it's starting to be, I understand that, you know, in some regions 250 euros is still expensive, I get it, but we're trying to make it at a price that it starts becoming, you know, a bit more of a no-brainer for, you know, at least for the engineers and scientists in some regions. So, and there's a lot, and this link will, you can find all these technical details. I'll put the link under the video afterwards. Now, I did have a question that came in from a new member at university, wants to measure nitrate and ammonium, and wants to sort of know about, you know, what technology do we have about nitrate and ammonium. I'm going to be a little bit quick first of all, because Ali, Philippe, Hasim, you know, the Aftab, I think even Niku and Hayuni all know this, that, you know, at Zimmer Peacock we've been making nitrate sensors in particular for solving the problem of farmers adding fertilizers to the crops. There's a runoff because the nitrate is quite excess. It can often be in excess, and it runs off into the water courses or gets into the groundwater and causes blooms, algae blooms, and causes, you know, kind of dead zones in rivers and dead zones in the ocean near the outlets of rivers. So we're aware of this sort of over-fertilization problem, and we're obviously aware that, you know, it leads to also pollution of the water courses. And therefore we've developed a solution to that, which is taking the nitrate sensor and putting it in a rod format. And we've built telemetry so that we can kind of remotely monitor what the nitrate rod is looking at. So this is what the hardware looks like today, and it delivers these sensors at a depth of 60 centimeters and 30 centimeters, has the electronics, and it has the communication. Now the inquirer is more actually interested in monitoring water rather than monitoring soil. So we have most of our public data actually in soil, but the sensor also works in water because that's how we developed and test it. It's easier to test the sensor in water than it is to make up soil slurries or make up soil stacks and actually test it in soil. So even though we're focused on measuring the nitrate in soil, the technology works as well in water. And this picture here of 2A just shows you an early version of the rod where we actually had sensors at a depth of 90 centimeters in the rod in the soil, 60 centimeters in the soil, and 30 centimeters in the soil. And just for your interest, the electronics are also pretty well protected because we've essentially put the electronics underwater and kept them running, so we're pretty sure on the robustness of our electronics to liquid. So that'll make the electronic engineers smile. We do have these installed, so it's not just lab testing. These are out there in the field, and so they work well with photovoltaics. It's all pretty low powered. So I'm going to go a little bit quick now because many of you have seen this. So I'm just going to say, we've put these nitrates rods, let's say, in the soil. We've monitored the way the sensors respond to fertilization. We've measured the way rainfall affects the nitrate and etc. So we have a lot of information about this, and I would look at the ZP AgTech website regarding this. So I wanted to go quickly through that because so many of you have seen it, and I'm not going to. Yeah. So just if you're interested in the nitrate sensor, by the way, we do have a beta testing program, so you can sign up for that and try to become a beta tester for it. Little picture that I just happened to take it last week. So we opened up this new lab in Coventry, and because the inquirer was asking about the nitrate sensors, I just wanted to give you a sense of how much testing and development's gone into this. These are essentially 4 soil stacks, all with the hardware in them. You know, so this is kind of science on a slightly larger scale now. You know, there you've got buckets of soil, good Warwickshire soil, in buckets, and we're testing it there. Yeah, so I was just saying that the nitrate sensor is a bit of a USP from Zimmer and Peacock, and he's right. It's you know, it's a unique selling point. I mean, this nitrate sensor, you know, and from it we can do a derivative of the ammonium sensor or the potassium sensor or the phosphate sensor. Yeah, I mean, it's really is one of the futures of humanity, both for soil testing and for water testing as well. And as I say, if people are interested in it, have a look at the ZP AgTech website. There's a beta program which people can join. The nice thing about the beta program is it's free, but it is by selection, I'm afraid. This was a really good one from a good friend of the company, Selsuk. He was just asking, you know, I think he was asking, he wants to measure essentially proteins at quite low concentrations. He wants to measure them in the range 0.1 to 25 nanograms per milliliter. And he's wondering about nanostructures and nanoparticles. And I think he's picking up on a video that we sent out a few weeks ago where I said, in fact it was last week, you don't need complexity necessarily of, in that last week we were talking about, here's a carbon surface, here's some nanoparticles on top of it, but the users were actually having problems because they couldn't do reproducibility. And I said, look, if you're going to use gold nanoparticles, just go for a gold electrode. So I will say the same to Selsuk here as well. Don't bother going for nanoparticles on, you know, on carbon. Just go for gold. And when I looked at the concentrations he's interested in, you've all seen this data a lot. But look, let me just remind you, when we were doing this work, here we've got 5 nanograms, and here we've got 25 nanograms. So here's the 5 nanograms per milliliter data, and here's the 25 nanograms per milliliter data. So you can see that there's a difference between these two data sets. So I really think quite strongly that the only part of this data we don't have is 0.1. So Selsuk's interested in 0.1, but I really suspect that if we did it, we would have had a curve that was essentially down here. So the answer to the question is, if you want to make biosensors, you want as few manufacturing processes as possible. So rather than go for carbon electrodes and then gold nanoparticles, and then, you know, I would just say just go for the gold and cut out a manufacturing step. And I think our own data shows that actually you could be successful doing that. And we've not done it yet, and I need to look into this a bit deeper, but I think the Sensit Smart actually has EIS capability, which is, you know, offers you a low cost option as well. Right, 8:29:52 seconds. So let me just summarize up a little bit. If you want to build custom cartridge inserts, we have covered that this week. I say start with a spectrometer and build it out from there. The question regarding the EasyFlex, I said, you know, honestly, don't buy the EasyFlex. I think you actually need a more functional potentiostat. I think you need the Sensit Smart, and you'll have to strap the Sensit Smart, put the Sensit Smart into a smartphone, put the smartphone on a wearable sports band, and if you follow the links, you'll be able to buy a cabled system from us, and then that will kind of give you a cable between the Sensit Smart and the biosensor. For cell 6 question, I'd say just go for gold electrodes. For the E-tongue, we have put that ZP ISC OEM solution out there. So you can buy a single board for 250 euros. So that means you could start getting going. You know, you could buy a pH sensor, a single board, and really get going now. And then you buy a second board and a third board, and that should sort of start building up the system. And then the nitrate and ammonium, I said to the Inquirer, she might be a bit surprised, but yeah, we've got an awful lot of technology around this, and really robust data. It's probably worth taking a look at the ZP AgTech site and seeing if you qualify. Yeah, really. Well, Philippe, thank you for that. Yeah, Philippe was just saying it's good to see these AgTech applications. Yeah, we really believe in AgTech and water tech for the future. All right, guys. Sorry to kind of tie you up for so long, but thanks all again. And yeah, stay in touch. So we'll do this again next Thursday at 8 a.m. All right.